Hello, today I will solve IMO Shortlist 2018 problem N1, which was one of the hardest N1 in the IMO history. In this problem, we need to determine all pairs of positive distinct integers n and k such that there always exists a positive integer s such that number of divisors of s times n and s times k are equal. At first, to solve the problem, we need to find how to compute the number of divisors for every number n. If we are given prime factorization of n, p1 to the alpha 1 power, p2 to the alpha 2, all the way up to pt to the alpha t, then number of divisors of n is given by the formula of alpha 1 plus 1 times alpha 2 plus 1 times all the way up to alpha t plus 1. I have already discussed this formula in the previous videos. I will link them in the description. If you got any questions about it, you can look at the video. Similarly, let's take k, p1 to the alpha 1, p1 to the beta 1, p2 to the beta 2, all the way up to pt to the beta t. Here in this problem, p1, p2, all the way up to pt are all the prime numbers which divides either n or k. There may be one of their powers may be 0. So this means that p to the I does not divide either k or n. So the number of divisors of k will be equal beta 1 plus 1, beta 2 plus 2, 1, all the way up to beta t plus 1. At first, notice that if one of the numbers is the divisor of the second one, such as can't be exist because let's assume that n divides k, s times n also divides s times k, and number of divisors of sk will be more than number of divisors of s times n. So in this case, number of sk is more than number of divisors of s times n. And the answer is for all other numbers, if k and n doesn't divide each other, we get that we can always find such s. And how can we construct this s? At first, notice that if we are given two numbers like p to the alpha py to the alpha y divides n and py to the beta y divides k, and if alpha y equals beta y, nothing will be changed if we take s multiple of py. So we can say that s has any distinct prime divisors from py. And if we add any prime divisors which is not in the set of prime divisors of n and k, nothing will be changed for number of divisors for s times k and s times n. They can't be equal if they are not equal before. So we have concluded that in the prime factorization of s, we need to take numbers like p1, p2, all the way up to pk, and they may have powers like gamma 1, gamma 2, all the way up to pt, gamma t. And now we need to discuss two different sets. The first set will be called this A set. We have indices. The alpha I is less than beta I. In this set we have like I. There we have alpha I is less than beta I. And for the set beta, B set, we have indices of I, there alpha I is more than beta I. And let's assume that size of A is some number m and size of B be some number L. And our aim is to construct new integers which will have some different type. Like, what can we say about the sum of the divisors, number of the divisors of s times n? This would be alpha 1 plus gamma 1 plus 1 times alpha 2 plus gamma 2 plus 1 times all the way up to alpha n plus gamma n plus 1. And for s time k, that would be beta 1 plus gamma 1 plus 1 times beta 2 plus gamma 2 plus 1 all the way up to beta n plus gamma n plus 1. And in this case, we can take the ratio of these two numbers. If this equals to 1, we can split these two different subsets, like for the indices which are in A and for the indices which are in B. And now look at the first one. If we are given alpha 1 plus gamma 1 plus 1 over beta 1 plus gamma 1 plus 1. Is it possible or not to take this value as something like t over t plus 1? Yeah, t is a enough big number. And now take their cross product. And what will we get? To find gamma 1. T plus 1 times alpha plus t plus 1 plus t plus 1 times gamma 1. This equals t times beta 1 plus t times gamma 1 plus t. Now if we erase common terms, we have gamma 1 here. Gamma 1 equals t times beta 1 minus t plus 1 times alpha 1. So I need to write alpha 1 here. And minus 1. And if we see that if we take t, if t is more than beta 1, then we can see that this gamma 1 must be a positive integer. So we can always find gamma 1 for large enough t if we know that beta 1 is more than alpha 1. And now, how can we use this fact? Because we know we can take t as large as we can, this will give us a lot of new chance to solve the problem. Now, look at the numbers which are in A. Like if we are given a alpha plus gamma I plus 1 over bi plus gamma I plus 1. This may take any value for m over m plus 1 for some integer m. And how can we apply this into our problem? If we take the product of the integers, like I, like that, and it will be easier to write elements of A, B, C1, C2, all the way up to Cm, because we have only M elements in A and we have only L elements in B. And for B it would be D1, D2, all the way up to DL. And so for the A elements we can take like alpha C1 plus gamma C1 plus 1 over beta C1 plus gamma C1 plus 1 if this number equals t plus 1 over t. Then if we take for the second one alpha C2 plus gamma C2 plus 1 over beta C2 plus gamma C2 plus 1, this number must be equal t plus 2 over t plus 1. And why is this good choice? Because if we take their product, it will be t plus 2 over t plus 1. how can we apply this into our lemma? What will be the total product? Their product, like I is from 1 to m gamma c1 plus alpha c1 plus gamma c1 plus 1 over beta c1 beta ci, sorry, we need to write I here, beta ci plus gamma ci plus 1. This would be t plus m over t. And if we write the same thing for the elements of B, for B elements, we get product from I equals from 1 to L alpha d1 plus gamma c1 gamma dy plus 1 over beta dy plus gamma dy plus 1. This would be, in this case, this would be the product from I equals from 1 to L m over m plus I. And clearly we get m over m plus L. And our aim is to find m and t, so big integers such that t plus m times over t multiplied by m over m plus L, this must be equal to 1. And what can we say about m and t? If we take their product, we get like tm plus te, tl must be equal tm plus m, small m times big M. We can erase this one. So t over e, t over m, big M, must be equal small m over e. And clearly we can always take two very big integers, t and m, such that their ratio will be some number m over L. So if we plug in this into our problem and use these substitutions, we can take these new integers s and s times n and s times k, who will have the same number of divisors. So the main idea in this problem was to use somehow this formula for a number of divisors and then try to think how to construct new integers whose ratio of the number of divisors for each prime p will be t over t plus 1. And then we need to split this set into two different ones, a and b, such that prime powers which divides n was greater than the a1, and prime numbers whose power divides more k must be in the b. So this was all I want to discuss for today. If you got any questions, please write in the comments and don't forget to like and subscribe my videos.